Good morning, grade 12s. Okay, so where we left off is at 4.2, and we're going to continue on from there. The main concepts that we've talked about so far in 4.2 are about the concept of intersection and unions. So just a quick refresher here, an intersection and a union can only happen when I have two or more sets that I'm talking about. It's possible that an intersection can be an empty set and have zero elements involved. But that's not always the case. An intersection is formed when I have two or more sets that have at least one element in common. I'll see this in a picture in my Venn diagram by seeing my two circles overlap, okay? Whether that's overlap a little bit where the circles are just passing through each other, or it's overlap fully where I'm completely one set is a subset of another. I'll have an intersection in both cases. I will not have an intersection, or I'll have an empty set of an intersection when my two sets that I'm talking about are disjoint, which means by definition they don't overlap at all. Okay? When I talk about a union is pretty much never an empty set unless the two sets I began with were empty themselves. A union talks about this new set in which it is filled with all of the elements that were in at least one of the two previous sets. So we use the word or to talk about union, but remember the word or when we talk about union is different than the word or when we talk about options, right? If I said, would you like ice cream or a brownie? In math, I'm not talking just about ice cream and just about brownies. I'm talking about the possibility of having both as well. So the word or means at least one of. All right. So we had started an example about cards, and we've introduced these 5 sets. The universal set of all cards, then clubs, hearts, spades, and diamonds, and we've talked about what was in each of them as well. We're just going to continue from here. So in each of the following questions here, it's still referring to the sets we've created. So it asks us, what does the union of spades and hearts relate or refer to? And then determine the number of elements in that union. Okay, so first let's define it. It says the union of S and H. So union is this symbol here. And I want to talk about what it refers to. Well, the union of S and H is equal to the set of cards that are spades or hearts. Now, if I think about it, in my union, there are cards that are spades. There are cards that are hearts, but there actually are no cards that are spades and hearts. So I could say cards that are at least spades or hearts or both. Okay, I could be a little bit more specific. That works too. Using the word or really helps when I'm defining a union. But in this case, there are no cards that are both spades and hearts, so it's a little bit easier here. There are no overlap between the two sets, which means the number of elements in the union of spades and hearts is, well, there was 13 spades, there are 13 hearts, and there is no overlap, so I'm going to have a total of 26 elements. Ooh, look, the next question is about an intersection of spades and hearts. So when I talk about the intersection between spades and hearts, I'm using this symbol here. And I could refer to it as the set of cards that are spades, and hearts. Now, I kind of just talked about this, but I know that that is an empty set. So I can also, below it, indicate this. Or I could use the other way of denoting an empty set. The 0 with a line kind of slashed right through it. That's an empty set. There's no elements inside of it. Which makes my next kind of answer pretty straightforward. If I'm talking about the number of elements in the intersection and I know the set is empty, there are no cards that are spades and hearts, that means the number of elements in that intersection is 0. Okay. Next question here. It says, are the events that are described by sets S and H mutually exclusive and or disjoint? Explain how you know. So remember, disjoint is kind of like that base level. It just means that there is no overlap between the two of them. And in this case, there is no overlap. The spades circle in my Venn diagram will not be touching the hearts circle in my Venn diagram. Mutually exclusive is like a level up of disjoint and asks, well, is it possible to have a card that is spades and hearts? Well, in this case, no. It's not possible to have pick up a card and it be both spades and hearts. Those cards don't exist in the deck, okay? And those cards aren't going to be made because the whole point of suits is to organize your cards into possible sets, and those sets are mutually exclusive. Okay, so let's write that down. Are the events that are described by sets S and H mutually exclusive and are disjoint? Explain how you know. So I'm going to say, since the intersection of sets S and H, so spades and hearts, is an empty set, we know they are disjoint. Okay. That's one part of my answer, but not the whole thing because I haven't said mutually exclusive yet. But the sets are also mutually exclusive since it is not possible for one card to be both a spade and a heart. Okay, so I know they're disjoint just because they don't overlap, and I know they don't overlap because their intersection is empty. But I know it's mutually exclusive because it is not possible for that to be true. It's not possible for a card to be both a spade and a heart. Okay, last question. What does the complement of the union of spades and hearts refer to? And then I want to know the number of elements in that set. Okay, so if we're talking about the complement of the union, something that's really important to talk about is that if I want to indicate that, I need to have the union fully in brackets and I'm taking the complement of that set. I cannot write it like this because this looks like the union between spades and not hearts. It looks like in this case that the complement is only applying to hearts, but I want the complement to be applying to the whole entire union. So it's really crucial that when I'm writing that down, I'm involving that set of brackets to indicate what the complement is being applied to. Now let's talk about it. A complement is all of the elements that is in the universal set that are not part of the set that I'm taking the complement out of. So a complement of the union are all of the cards in my deck of cards that are not part of that union. Okay? So we know the union is every single spade and every single heart. So the complement of that union would be all cards that are not spades or hearts. Right? And if we look back to the definition we've created for the union, really I'm just adding the word not in there because it's all of the cards of the universal set that are not part of that original union. Now, for this particular question, we can actually very easily classify what the rest of those cards are, right? If I'm talking about all the cards that are not spades or hearts, in this case, realistically, that complement refers to all cards that are diamonds or clubs, right? Because that's the remaining set of cards. Referring to it in that second way is not necessary, but really helps us with the next part of that question. So whatever I have in blue is kind of the most pertinent in terms of my answering that first part of the question, what does the complement of the union refer to? But the second part really helps me with determining the number of elements in the complement of the union. Yes, that second set of brackets is necessary because I always have to put my set that I'm taking the number of inside, and that set already involved brackets. The second set of brackets is just part of the proper notation of the number of elements within the set. Okay, so if I know that those are all the diamonds and all the clubs, yeah, those are all four of those things. All the diamonds are all the clubs. I know that there was 13 diamonds and 13 clubs, so I have a total of 26 remaining elements. Remember when we were talking about the complement, another way to calculate that is to take the number of elements in the universal set and subtract the number of elements in my union. We kind of did this with the triangular numbers for T complement. There was a question in your previous practice about set X, which wasn't defined to us, but information was given about it. Which means I can just plug in those other numbers that I already know. I know that there's 52 cards in my universal set. I know my union had 26. And I'll get 26 there as well. So I don't need to know the specifics of my situation to figure out the complement of the union and how many elements are in there. I can use my other information, my universal set numbers, and my union numbers to figure that out. Okay, so that was intersection, that was union. There's one more bit that we're going to be talking about today, and that refers to the subtraction of sets. Now, the subtraction of sets, again, is a little bit ambiguous in terms of its definition because we're not always performing straight up subtraction, but we're going to talk about what that means, and I think it'll make sense once we refer to the definition. So the subtraction of sets is the set of elements in one set that are not elements of another. The symbol for it, the notation for it, happens when I have two sets, just kind of like intersection and just kind of like union. I can't have a subtraction of sets when I don't have at least two sets. And this is the symbol. This is kind of like the minus sign for sets. And again, it's not referring to straight up subtraction, like 5 minus 2 is 3, not always doing that type of subtraction for sets in particular. And I'm going to write that down just so that you can reference it, that it is not always found using straight subtraction. Okay, now let's talk about two sets. And I'm just going to make up some elements in a set. Here I have 3 pictures. And this is kind of like the 3 kind of ways sets can relate to each other. Now, of course, in this picture, I've drawn B to be a little bit smaller, but you'll notice in all 3 pictures, set A is the same. In all 3 pictures, set B is the same. I'm not really changing anything. I'm just changing where they're placed. In the first example, I have B being a complete subset of A. Okay? Now, I'm going to make up some sets just for us to kind of picture. And I'm going to make up 3 different examples because I can't have one example where B is fully an A, B is somewhat an A, B is not at all an A. So I need to make 3 different examples if I'm ending up with 3 different Venn diagrams. So I am going to, define A as the set of digits. I guess I don't really need to write the set of. I'm going to write A as all digits. Let's make U the set of all numbers from 0 to, let's say, 11 inclusive. Again, I'm just making up examples here. So if you're wondering where these sets came from, just the top of my head. And in each of these 3 examples, I am going to swap out what B is. Okay? So in the first example, I know B has to be a subset of A. So I'm going to define B as 0, 1, 2, 3. Okay? And now let's just for funsies fill out where all those numbers go. I know 0, 1, 2, 3 all belong in B, which also all belong in A. I need to know that A still has additional elements inside of it. So 4, 5, 6, 7, 8, and 9. And I know the universal set includes the remaining elements, which are 10 and 11. Okay. Now let's talk about the subtraction of sets. So I have A, but not B, or A minus B. I also like to think of the subtraction symbol as referring to but not including. So when I take a look at this, I'm looking at all of the elements in A, but I do not include the elements that are in B. So if I'm taking a look at the subtraction of sets here, all of the elements in the A circle, so all of these, let me use a highlighter instead, all of these, but I do not include anything that's in B. So my elements in my set, A but not including B, are 4, 5, 6, 7, 8, and 9. The number of elements in that set I've just created is 6, right? 4, 5, 6, 7, 8, 9. There's 6 elements in that set. Oftentimes, if I'm trying to figure this out with a Venn diagram, I will literally take my pen, my pencil, and I'll cross out the elements in that second set to just remind me that they're not included. Okay, I hope that makes sense. So elements in A that do not include elements that are in B. All right. Next example. So I'm going to maintain the universal set. I'm going to maintain what A is as a set, but I'm going to redefine what B is. So let B, I know I have to have some overlap, but B is not fully in A. I'm going to let B be the set of numbers 9 and 10. It's a small set, but I know that there's some overlap with A, but not fully overlap. And I'm going to put those numbers, again, back in my Venn diagram here. So I have 0, 1, 2, 3, 4, 5, 6, 7, 8, all just in A. I have that 9 belong to both A and B. I have 10 belonging to B. And that 11 is just floating around in the universal set. Okay, same idea as before. I want to know all of the elements in A that do not include the elements that are in B. So all the elements in A are what I've highlighted in yellow. And I'm not going to include any value or element that is also in B. So I've crossed all of B out just so that we're not including it. And that would be the set of numbers 0, 1, 2, 3, 4, 5, 6, 7, and 8. I am not including 9 because 9 is part of B. And I do not want to include the elements that are part of B. I can also find the number of elements in the subtraction of those sets, which is, I can count them, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, last but not least, final example here. I've defined A in my universal already. I'm maintaining that same definition. Now I need to define B. I'm just going to define B as the number 11. Okay? Again, I can put all of those elements in my picture. So I know 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9 go in set A. I know that in set B would be 11, and 10 is floating around. Okay. The set of all elements in A is this yellow circle. That are not in B means I'm crossing off B here, which actually still happens to straight up B, the same as all the elements in A. Because there is no overlap, when I choose to purposely not include set B, it has no impact. Because all the elements that were in A that aren't in set B already were the same because of the lack of overlap, because these sets are disjoint. So the number of elements in A that are not in B is equal to 10. This is why I had that caveat at the very beginning. Here, I'll maintain this coloring so we can look at it later and kind of understand it a little bit better. Okay. This is why I'm saying it's not always a straight up subtraction. Because in this case, I always had 10 elements in A. And here I have 4 elements in B. 10 minus 4 does give me 6. So sometimes it can be subtraction when I have a subset of another. But in the second example, the middle example, I know I have 10 elements in A, but I have 2 elements in B, but 10 minus 2 is not 9. So I was not using straight up subtraction to find the number of elements in that set when I was overlapping, but not a subset. And in the last one, I had 10 elements of A. I only had 1 element in B. 10 minus 1 is not 10. I didn't do subtraction at all because there was no overlap, because the sets were disjoint. So when I take a look at the subtraction of sets, like I said at the beginning, it is always sometimes a little bit ambiguous, a little bit confusing, because we're used to subtraction as straight up minusing numbers. I'm just thinking of subtraction of not including certain numbers. And those particular numbers, or elements, it doesn't have to be numbers particularly, belong to that second set. So I like going through this method of, in my Venn diagram, highlighting the ones from the first set and crossing out all the elements in the second set so I can better count or visualize what I've got here. All right. We have one more example that we're going to do, and that's it. So I have this universal set that a rec league offers all of these activities below. So this would be my universal set. All of these different sports: badminton, rugby, cross-country skiing, basketball, soccer, cross-country, golf, ultimate softball, hockey, volleyball, field hockey. Now we are going to define 2 additional sets in part A. So the first set is set B, the set of activities that includes a ball. So let's take a look at this. Rugby involves a ball. I don't know why I started at rugby. I think because mentally I know that badminton didn't. So badminton is not part of set B. There's no ball in badminton. Okay. Rugby does have a ball, so rugby is going to be part of set B. Cross-country skiing, no ball. It's out. Basketball, yeah, it's right there in the name. Soccer, you betcha. Cross-country, no, that's just running. Golf, yep. Ultimate, no, that's the game where you just use frisbee. Okay. Softball, yep, again, right in the name. Hockey, no. Volleyball, yep. And field hockey, also yes. Field hockey is similar to hockey in the sense that you have a stick and you are hitting something with it that you're trying to score in the other team's net. Except in field hockey, it's a ball because you put it on a field and a puck wouldn't slide or move nicely on grass. Okay? So they use a ball and a stick. So that's what I have for B. Set I, the set that uses an implement. An implement, and you could ask this on a test if you didn't know what the word was, to be honest, that's totally fine. An implement is just something that you hold that you are going to be using to hit something else, or to just have in your hands to assist you in the sport. Okay? So something that you're holding, kind of like a stick. So if you were playing hockey, hockey would have an implement because you're holding a stick that's going to assist you in the sport. It's going to assist you in scoring a goal, etc. A racket can be an implement. Poles can be an implement. Anything that you are holding constantly to then use to help support you in that event. So if I'm going through this, badminton has a racket that you hold the whole entire time that helps you hit the bird across the net, so it has an implement. Rugby, there's nothing you're holding the whole time. Cross-country skiing, yep. You are holding poles that are helping you the whole entire time. Basketball, no. Soccer, no. Cross-country, so just running, no. Golf, yeah, you're holding a club. Ultimate, no. Softball, yeah, you're holding a bat. Hockey, yeah, you're holding a stick. Oops. Hockey. Volleyball, no. Field hockey, yeah, again, you're holding a stick. Okay. With that being said, we need to do 2 things. We need to draw a Venn diagram. And then we need to figure out the number of elements in each of the following sets. So the Venn diagram is going to be helpful to draw first. And what do we draw first? Totally, it's a box with my universal set. What's next? Well, my 2 sets B and I And if I look at this, I'm going to be making sure to draw this big enough because I'm actually going to write all the names of each of the sports inside my Venn diagram so that it could really help me determine the number of elements in each of these regions, each of these sets. Okay, so I know set B and set I will overlap. I know they overlap because since we've defined the sets B and I above as a list, I can very easily see that there are some elements that are common between the both. So golf is in both. Softball is in both. Field hockey is in both. So as I draw my Venn diagram, I'm actually going to start with the commonalities. Actually, before I do that, I noticed I drew my circles a little bit too big. So I need to have room on the outside of my box as well, because I'm sure there's some events that are not in either of them. All right, so if I'm drawing my Venn diagram, I know golf, softball, and field hockey are going to go in the intersection, in the overlap between the two sets. If I'm looking at my B circle here, this circle, this is all of these sports. I've already written down the 3 sports that are in both B and I. Now I'm going to write the remaining sports, so rugby, basketball, soccer, and volleyball, just in the section of the B circle that does not overlap with the I circle. So, rugby, basketball, soccer, and volleyball. Now, in my I circle, these are all of the sports that belong to I. But badminton, cross-country, ski, and hockey are the 3 sports that belong just in I and not in B. So I'm going to write those down. Badminton, cross-country, ski, and hockey. Now, if I take a look at the greater picture, all of these sports are in my universal set. So every single sport should belong inside that box. Now, I've already involved badminton. I've already involved rugby. I've already involved cross-country ski. I've already involved basketball and soccer. But I haven't involved cross-country yet. So I'm going to write cross-country in my box, but not within my circle, because it's still part of the universal set, so it still has to be in my picture. But I haven't written it down, so it's not in B or I, so it has to go on the outside. So now I've written down cross-country, yay. Golf I've included, ultimate I haven't included yet. So I need to make sure that that also gets included. Ultimate. Okay, now that's good. Softball I've involved. Hockey, volleyball, and field hockey I've involved. So my picture is complete. My Venn diagram is complete. And this is really going to help me answer all these follow-up questions, because all I have to do now is count. So the number of elements in the universal set, set B, and set I can either count straight up from my Venn diagram, but I've also listed them all above, so I could also count them based on the list I've provided. So the universal set is going to have 12 different sports, because that's what's in my list, or I can count it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Either way, I should get the same answer. The number of elements in set B, well, 1, 2, 3, 4, 5, 6, 7. I'm expecting 7 here. The number of elements in set I, 1, 2, 3, 4, 5, 6. Oh, haha, oops. Okay. common mistake when I have an element that's multiple words. I accidentally underline cross and then country ski. This is just one. 1, 2, 3, 4, 5, 6. All right. Now we're looking at some complement stuff. So, what I like to do when I think about complement is I like to highlight that set first. So, I'm going to do a whole bunch of highlighting. I'm going to erase that highlighting after. So, please don't feel like you have to highlight and then now you're stuck. But just kind of picture things with me. So, if I want to know the complement of set U, I'm going to first start by highlighting set U, which is everything. Now, a complement is everything in my universal that's not in that particular set. But the number of elements in my universal that are not in my universal doesn't make sense. Essentially, it's all of the sports I have not highlighted, which is none. I've highlighted them all. The complement of the universal set will always be 0 because the universal set refers to all elements, so the complement is always going to be 0. Okay, let's take a look at the complement of B. So if B is this circle here, the complement is everything that I did not highlight within my universal set. In this case, I can see it's not going to be an empty set. There's actually going to be numbers here. And again, I could do this in 2 ways. In my Venn diagram here, I can just straight up count. I can go 1, 2, 3, 4, 5. So there are going to be 5 elements within my universal set that are not within B. But also mathematically, I can do this pretty easily as well, right? The number of elements in a complement is just all the elements in my universal. Subtract all of the elements or the number of elements in my set B, which we've already know those numbers. We know 12 and 7, which gives me 5. So I could do it in either of these 2 ways. Regardless of which way I use it or complete this, I should get the same answer. All right, the next one. I can highlight all of set I, and then I can count, no problem. 1, 2, 3, 4, 5, 6. So I know my answer is going to be 6. But I can also do it in that other way. I know the complement of I, the number of elements in that, can be found by taking the number of elements in the universal and subtracting the number of elements in set I. And again, we know all those numbers. We know that it's 12 and 6, which will give us 6. So we've got options. Okay, now I'm talking about intersections and unions. Next 2 questions talk about intersections. So intersections, I've highlighted in yellow. The number of elements in that intersection, I can count. 1, 2, 3. The number of elements that are in the complement of my intersection are the number of elements that are not part of my highlighted piece. And again, I can count those. 1, 2, 3, 4, 5, 6, 7, 8, 9. Or I can say, didn't need a second equal sign there. Or I can say the number of elements in set U. Subtract the number of elements in the intersection, which we know is 12 and 3, which also gives us 9. So always a second option for determining the number of elements in the complement. Okay, last but not least, now we're talking about unions. Unions are all the elements in at least one set. So this is at least B. This is I. And I can go and straight up count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 elements that are in the union of B and I. And again, to find the complement, I'm just looking at all the areas that are not highlighted. So cross country and ultimate, there's 2 of them. Or I can go ahead and say the number of elements in the universal minus the number of elements in the union, which is 12 minus 2, which is, 12 minus 10. That's a boo-boo. 12 minus 10, there's the 10, which is equal to 2. Oi, yoy, yoy. Okay, that question does in fact continue to the next page. So just to allow us not to flip back and forth, I'm going to bring this picture over here so we can finish the question and still be able to refer to it. I'm going to get rid of the highlighting though. Okay. Now we've talked about intersections, we talked about unions, we talked about complements. Let's talk about some subtraction stuff here. So determine the number of sports that require the following. So I'm looking for the number of sports. I'm looking for n of something for all of these. And I want to use proper notation. So I can't just write n of and then literally write a ball but not an implement. Okay. So I'm going to use proper notation. So a ball, but not an implement. So if I wanted just the number of elements that involve the ball, that would be n of b. But I do not want to include elements that involve an implement. So sports that involve an implement. So when I do this, again, I'm highlighting and I'm going to cross out, but I'm not going to keep it there. I'm going to erase it after. But if I'm looking at that, this is all of the sports that involve a ball. And like before, we're going to cross off or not include all of the sports that involve an implement, which allows me then to count. 1, 2, 3, 4. So my answer is 4. There are 4 sports that involve a ball, but do not involve an implement. The way that's phrased, ball but not an implement, also refers to just only a ball. Okay, question 2. The number of sports that involve an implement, so all of these, but do not involve a ball. So I'm going to take out all of these options. So implement, but not ball. And I can count. 1, 2, 3. Okay. The next one, the number of elements or another sports that involve a ball and or an implement. Okay. So I'm wanting to include the intersection. And I'm wanting to include just ball and just implement because or can mean either or both, and means both. So these are the regions I'm interested in. Well, hey, if I want to use proper notation, that's just the union. That's what my union looks like, at least one of. So at least a ball or an implement. And we've actually already found this information on the previous page. I'm just making you find it again so you can understand what it means in words. And if we do this, well, I know that that's still 10 because I can still count. Or I can look back and look at what I got before. But it's the same information. Now in the last one, it's saying the sports that involve neither a ball nor an implement. So if I take a look at this, first of all, sometimes just in context, I know the answers to, right? Because cross country and ultimate on the outside are not in the ball or implement brackets. Or not brackets, circles. Which means I'm talking about the sports that don't use a ball or don't use an implement. Okay? Specifically when they don't use both. Now let's talk about notation. I technically have options. So if I'm talking about the region where I'm going to find my answers here, I'm talking about this outskirts region, which kind of looks like the opposite of the in regions, right? Everything that I've done in purple is not what I've just done in yellow, which means I could be talking about a complement of the yellow stuff. Well, the yellow stuff is what I just had in the previous question. It was the union. So if I want to use proper notation, option number 1 is I can say, you know that union, that yellow thing? Everything that's not yellow, which would give me everything that's purple, which would give me the space I'm interested in, which would give me the number 2. Another way I can do this or think about it, and again, we're looking at this just for the first time, so if you're like, whoa, that's kind of crazy, totally fine, we're going to look at it all at once. Another way I could look at it is I go, okay, I want everything in my universal set. But I don't want to involve things that have a ball. And I don't want to include things that involve an implement. So I can write this as a subtraction. I can say the number of elements that are in my universal that are not part of set B and that are not part of set I. I've taken away 2 regions. So everything in the universal, don't include the ball set and do not include the implement set, which just leaves me with 2. Okay, this is it. That's 4.2. There's some practice that follows. Please tackle it. Just a reminder, there's a quiz after 4.3, so it's not coming up soon, as in like tomorrow or the next day, but probably coming up either end of week or early next week, depending on when we finish 4.3. So just have that in the back of your head. That is it for now. Have a great day. Bye.